If you look around you right now at your car, an airplane flying overhead, maybe even the can you're drinking from, it was almost certainly shaped by metal forming.
Things like rolling, forging, stamping, it's really the backbone of modern engineering.
Absolutely. But here's the dirty secret. A lot of the time, optimizing these processes is still based on slow, expensive trial and error experiments.
It almost has to be. I mean, modern manufacturing is pushing materials like aluminum to their absolute limits.
You're talking about severe plastic deformation, right?
Exactly. We're using multi-pass processes where the direction of force changes halfway through, and you're dealing with these huge temperature swings.
So something like equal channel angular pressing, ECAP, for example.
That's a perfect example. The physics are so complex that, failures, wasted material, and just long debugging times are a constant headache.
Right. We can't just rely on physical tests anymore. We need powerful mathematical blueprints to simulate the whole thing on a computer.
And that's what brings us to our deep dive today. We're looking at a huge step forward in this area, a modified two-level statistical constitutive model, or CM.
This one was developed by Vyshkovova and her colleagues, right?
That's the one. It's built specifically to describe how aluminum, which is a common face-centered cubic, or FCC, polycrystal, behaves under these really complex loads.
And crucially, with simultaneous temperature changes.
Yes, that's the key. It's the bridge between what you see on the macro scale, the final shape of the part, and the micro scale physics, what the atoms are actually doing inside.
Okay, so let's unpack that. If this new multi-scale model is such a breakthrough, what was so wrong with the older models? Why did they fail when things got complicated?
They failed because they were essentially blind. The standard model was what we call macroscopic phenomenological model.
Okay.
And look, they're computationally fast and they work just fine if you're running a simple unchanging process. But they treat the material like a black box. They see the bulk behavior, but they don't look inside.
So if I start rolling a sheet of metal in one direction, the model is happy.
Perfectly happy.
But if I then switch it up, say, I want to stamp that sheet into a car door, changing the deformation path, the model just breaks.
Precisely. It breaks. Because those macroscopic models don't have an explicit description of the internal structure, you have to completely redefine their parameters every time the loading path shifts. They just can't predict what happens inside the metal once it's already been strained.
And that's the killer, right? That's why they miss the microstructural evolution that actually determines the final quality of the part.
Yes.
So what are those, telltale effects that the old models completely miss?
Oh, huge mechanical effects. Things like stress dives right after a path change where the material suddenly seems to soften.
And what about cross-hardening?
And cross-hardening, where pre-straining it one way makes it much stiffer in another direction. They also completely failed to describe how the shape of the yield surface changes.
The yield surface. Okay, for listeners who aren't engineers, how should we visualize that?
Think of it like a safety boundary for the material. Any stress combination inside that boundary, and the material is elastic. It just bounces back.
But if you go outside that boundary?
It yields. It permanently deforms. And for the old models, this boundary was often way too simple, like a fixed sphere.
But in reality, it's not like that at all.
Not at all. It's more like a rubber band ball that changes shape every time you squeeze it. And that changing shape is what dictates how the metal will respond to the next step.
This is where it gets really interesting then. The advantage of this multi-level constitutive model is that it actually includes the physics of what's happening at different scales.
Yes, the macro level and the meso level. So you get a single model with one set of calibrated parameters that can handle all these different conditions.
We're moving from just describing what we see to tracking why it happens.
Exactly. So this specific model is a two-level statistical CM for FCC polycrystals, like aluminum. At the macro level, you have the representative volume element, the RVE. That's the bulk material.
And that RVE is made up of a bunch of individual grains. The paper says 343 of them.
It does.
Why that specific number? Is that just the computational sweet spot for balancing accuracy and speed?
That's exactly right. Because it's a statistical model, they're prioritizing efficiency so they can describe large industrial-sized products. So the relative arrangement of those 343 grains is, omitted.
But they still track how the grains rotate.
They do, using the Taylor hypothesis to average it out.
So instead of getting bogged down in every tiny interaction, you're tracking the average physics inside a representative chunk of metal. What are the most important processes to track at that grain level?
The main one is what's called intragranular dislocation slip.
Which is basically the movement of internal atomic defects.
Yes, the movement and pileup of those defects. The model also tracks grain rotations, how those defects recover or even annihilate each other, and the resistance from grain boundaries. That's the Hall patch effect.
Okay, that sounds pretty comprehensive for simple loading, but what about when you suddenly reverse the strain? They had to modify the model for that, right?
They did, and this is critical. They added a specific term to the hardening law, which they call K-reversal.
K-reversal.
You can think of it as the model's built-in dislocation reset button. It specifically measures how quickly those built-up defects disappear when you flip the direction of the force. It's absolutely essential for modeling things like the Bauschinger effect.
So with all of that built in, how did it perform? How accurate is it?
They validated under simple shear across a huge temperature range, from a very cold 153 Kelvin up to hot forming temperatures of 573 Kelvin.
And the result?
The result was, for direct monoconic loading, the calculated flow stress had a relative deviation of less than 2.9% from the experimental data.
Wow, less than 3%. That's stunning fidelity for a model that's tracking physics from the atomic scale all the way up.
It really is.
But the real breakthrough isn't just that number, as good as it is. It's what the model let them see inside the metal. What did tracking the active and near-active slip systems actually reveal?
This is where you get the real value. You see, when the material first starts deforming, the model shows that lots of the crystallites have a high number of near-active slip systems, often 8 of them.
Meaning the stress is concentrated right at the sharpest points of that yield surface we talked about.
Exactly. The material is sort of ready to deform in many directions at once.
But as you keep straining it, that internal structure changes.
It does. The fraction of crystallites with 8 near-active systems goes down, while those with 6 go up. The material is undergoing what we call latent hardening.
So the initial strain creates its own barriers, making it harder for the original slip systems to keep going.
Precisely. The crystal lattice rotates, the yield surface transforms, and those easy pathways for deformation they cease to exist.
Okay, so let's move to that really common scenario, reverse loading. The model successfully predicts classic features like the Bauschinger effect.
Right, the drop in yield strength.
And that strange plateau you see in the stress strain curve right after the reversal?
Yes, and the deviation is still excellent. It's less than 7% for reverse loading. And the model lets us see why that plateau happens. It's because of the rapid annihilation and collapse of the defect substructures.
So the little dislocation loops that hadn't fully expanded in the first direction just collapse when you reverse the force.
Yes, they do.
It's like you spend energy building a structure, and when you switch direction, you first have to spend energy tearing that old structure down before you can build a new one. That's the plateau.
That's a perfect analogy. And the model shows a fascinating shift. After reversal, you see a sharp increase in crystallites with a smaller number of near-active slip systems, like 4 and 5.
Why is that?
It suggests that the barriers created by the pre-strain are actually perfectly aligned to be destroyed or activated easily in the reverse direction. So the material gets temporarily weaker until a new, stronger microstructure can form.
That's a vital insight for anything that undergoes cyclical loading.
Okay, what about orthogonal loading?
Mm-hmm.
So you pull it in tension, then you switch to simple shear.
A great test for the model. And when that path change happens, the number of crystallites with 6 and 8 near-active systems just plummets.
And the ones with 4, 5, and 7 increase instead.
Right. Because the initial tension fundamentally changed the material. It created a very specific set of strong, latent barriers. When the shear hits, the material's response is completely dictated by that preliminary tension.
Which brings us to the final piece of the puzzle, and maybe the most important for industry. Combining that load path change with a rapid change in temperature.
This is critical. Temperature directly governs how fast those defects can recover and annihilate. The model's real power is simulating these things happening at the same time.
So let's take rapid heating. We jump from a very cold 153 Kelvin to room temp, 293 K, right at the moment the strain path changes.
That temperature increase acts like an accelerator for the annihilation process.
So heating the material while it's trying to reorganize its internal structure leads to enhanced annihilation. The defects just disappear faster than they can build up.
And on the loading diagram, what does that look like?
It creates these extensive regions with weak hardening. The material just stops getting stronger for a while, which could be catastrophic.
So a manufacturer might think they're helping by heating a part for stamping, but they could accidentally be creating a weak spot right where the shape changes.
Exactly. The model predicts that precise outcome. Now, let's look at the opposite, rapid cooling.
Dropping from 293K down to 153K during the path change.
You get pronounced hardening. Immediately after the path change, the material gets much, much stronger.
Why? Because the cold is locking the defects in place.
It's locking them in place. The cold limits their mobility so they can't recover. That, combined with the structural mess from the path change, just magnifies the strengthening effect.
And the source notes this is not typical for orthogonal loading at a constant temperature. It's the combination of the two things at once that creates this dramatic effect.
It is the coupling of the two. This shows us that temperature isn't just some separate variable you can tweak. It's an intrinsic part of the material's structural response to complex loading.
So to sum this all up, this model by Vyshkova and colleagues, it's accurately describing aluminum behavior under these incredibly complex conditions.
It is.
It's handling the Bauschinger effect, the stress plateau, simultaneous temperature changes, all with an accuracy that's less than 3% off for simple loading and less than 7% for reverse loading.
And that accuracy means engineers are no longer guessing. They have an explicit microscopic description of what is happening, the rate of dislocation annihilation, the yield surface transformation, the exact moment latent hardening kicks in.
It's a move from expensive, iterative trial and error
to precise, simulation-driven optimization.
So think about this as you consider how materials are designed for critical stress points. The model clearly shows how thermal changes can either suppress hardening with rapid heating, creating a temporary soft zone, or drastically enhance it with rapid cooling during a mid-process strain path change. If you are an aerospace or automotive manufacturer, how might you use this precise predictive capability, this ability to turn a hardening almost on or off locally, to intentionally design a component where extreme durability is required right at a joint, or a specific high stress point, tailoring the material strength where it's needed most? That is the immediate, powerful application of understanding the microscale physics.